thank you for the introduction again. I'll be indeed presenting the session on robot vision for object grasping, and I'm from the Automation and Control Institute, the Vision for Robotics group that's part of it at TU Vienna. I'll be presenting the work of the entire group. That's a lot of people. As you can imagine, research is always a teamwork, and specifically, presenting on behalf of Marcus Vince, who's the professor leading that group. Okay, so first of all, quick word of what we mean by vision for robotics. There's basically two big axes. The first one is understanding objects through vision, and by object, in this case, we mean anything that can be interacted with by the robot. So typically in the kind of robots we consider, service robots or service robot in general, that's mostly mugs on a table, books in a bookshelf, and anything that can be grasped and can be manipulated with. And so the interaction that's necessary involves typically modeling the object. So that means obtaining some 3D representation of it, having some way of tracking that object through time, recognizing specific instances of an object, or at a higher level, understanding the class of the object, and any information you can obtain through vision to manipulate it. That's typically how to grasp the object. And the second axis, because typically the robots we consider, they're evolving in a given environment, it's very advantageous to also understand it and make use of that information. So I'm sure, given the audience, you're very aware of that, of course. And so, typically that means understanding rooms and relation between rooms and furniture, objects and furniture, so that down the line, when your robot needs to search for an object, it doesn't randomly search, but it can search more meaningfully, looking first at the table in the kitchen for a mug, or bookshelf in the office for the book. Some basic things, but that needs eventually to be. It can be entirely hand modeled, of course, but it can also be partly inferred from the vision sensor. Okay. Second of all, why am I not talking about computer vision and specifically about robot vision? There's a couple of differences. I'll be focusing on three. The first one is that, as mentioned, the robot will be evolving typically in a given environment. It's usually deployed in a fixed environment and moves for quite some time. You don't change the flat every other day, and so it makes sense to understand that. That can be done at different levels, of course. It's at the lowest level, it's necessary to understand it such that the robot can navigate through the environment, but it can also involve semantic knowledge. And you can see that in that one example, there's a noisy inference of what type of what class are all the points in that reconstruction. So that can be what's part of the floor, what's part of a table, what's part of a desk, what's part of a couch, and so on and so forth. And that's obviously useful down the line in all sorts of operations. Second of all, robot, contrary to just a floating camera, is embodied and has knowledge about its own body. And that as well is, of course, very important, specifically when we talk about grasping, because you have a set of sensors that enable the robot to know by itself through proprioceptive sensor, it can know the position of its end effector relative to the camera, possibly with some noise, but still have a pretty good knowledge of that, which, again, in the context of grasping, is very useful information. Finally, since we talk about robots that have to move in a space, 3D information, 3D data, 3D sensing, and geometry are much more common and a lot more to the forefront of our methods and reasonings. And in terms of sensing, you have a couple of different modalities, always their advantages and disadvantages, but it's a lot more common to have it in the beginning. So that can be, through stereo depths, like if you're familiar with it, the Z camera, or many different setups. Dot pattern matching, like the Kinect, or time of flight, like the newer Kinects or LiDARs, and a lot of giant cloud of sensors. But yeah, so really what robot vision is about is taking advantage of those specific facts about robots to adapt the method from computer vision and take advantage of all of that. All right. We won't go over the entirety of robot vision, of course, and today we're focusing on robot vision for object grasping. And specifically, you could just use your geometric sensing, your 3D sensing, and try to infer where you could place your end effector and pick up something without any knowledge about the scene or the objects, of course, but that has limited use besides just lifting an object and putting it somewhere else. At its core, that's more pick and place. What I want to focus on today is something more task-directed and object-oriented. And by that, I mean that, going through some understanding of the object first to then grasp it so that you can also grasp it more meaningfully. And that's the difference between just grasping a mug so that you can just lift it and move it around, and grasping a mug by the handle so that you can also pour some liquid in it and then use it for something, or grasping the bottle so that you can actually open the bottle down the line. So yeah, that of course requires some understanding and knowledge about the object. So the typical pipeline that we follow in for such kind of tests is to first detect the object, of course. Once you have a detection of the object, that can be either just a bounding box around it, or even, as you can see here, a mask that is just every point of the object, every pixel of the object is colored accordingly. From that detection, the goal is then to estimate the pose of the object in that scene. And so there's of course no absolute pose for any given object, but when we talk about pose estimation, it's just a relative transformation between the object in the scene and the reference object model that we have. So that rotation and translation from one to the other. And finally, once you have the object pose estimation, well, there's some verification that you can perform to have a better certainty, higher certainty of your grasp or your pose being correct, and how you go from that pose estimation to where you should be grasping the object. And this is typically just done from the object model and the knowledge you have about the object model, and through the transformation from the object model to the scene, also transforming the grasp approach you want to have. So the presentation itself will also be following the pipeline itself. So we'll go first into object detection. And yeah, this, I wouldn't consider it the core of the presentation, but I will still mention a couple of methods. And the first of all, that's kind of hard to avoid, but I still wanted to mention it. It's not particularly from our lab or anything, but it's very commonplace at this point, so still worth mentioning. And that's a big family of the Region CNN, Faster RCNN, and Mask RCNN, just all those state-of-the-art convolutional neural network-based object detectors, which you have two big classes in that family, which is the two-stage one, like the Mask RCNN one, where you have a convolutional neural network backbone that will be used to infer region proposals. So that's just predicting some bounding boxes on the image, and then a second stage to refine that bounding box and potentially also predict a mask around it. And another class family that does everything at once, just directly predicting the bounding box. Again, this is not particularly the focus of the presentation of today, but it's still very useful. I wouldn't dare to call it pre-processing, but for the sake of our presentation, it's just getting the information that we need, that is detecting a given object. And of course, in its standard application, you do object detection at the class level. That is, this is a person, this is a mug, etc., etc. But for our purposes, it's also very interesting to do it even at the instance level, so detecting that specific mug or that specific bottle, because you need typically down the line the model of that object to be able to estimate its pose and so on. So that makes actually the task a little easier. However, there's other options still, of course, to perform object detection. And in the case of robot vision, of course, as mentioned, we know our environment. And so we can take advantage of that to detect pretty much everything that is out of place. And so this method that was presented last Iros, or 2 Iros ago, basically builds on the fact that we can know our environment, and therefore we can build a reference map of the environment. And so in this case, by reference, we mean that it's the tidied up version of the room. So everything is where it should be. And then if you do that at the same time, at the once people have been lived in and objects have been moved, you will, of course, have a lot of differences in that reconstruction. You cannot directly compare reconstruction to reconstruction because everything is too noisy. Your sensor in the first place is noisy. Your camera poses because you have to track the motion of the camera to be able to reconstruct the scene. That also will be fairly noisy. So you can't directly go pixel to pixel. However, if you include some semantic knowledge in it, then you can go a little further. So that's what you see down there. Can you? Yeah, that's what you'll see down there, where every point in the reconstruction gets assigned a label, and so there's the floor, the desk, and everything. And using that semantic knowledge, you can, for example, say that you don't care about any points in the floor because that's not going to move. Any point of the table is also not super relevant. Of the chair, that's going to move, but you also don't really care about it. The problem is that most of those methods are going to be trained in large-scale data sets for semantic segmentation. That is, assigning a class for every point in the reconstruction. And those data sets have a couple of biases, which make them typically all the smaller objects in them are not annotated properly. So you will, if you just do that, you will lose a lot of objects because they will be annotated as part of the table, because the network was trained in such a way that it doesn't need to care about smaller objects in the scene or smaller objects on the table. So what you can do then is go back to something a little more classical, and once you have the table that you're interested in, you can do something called plane pop-out. That is just modeling the plane from the vision and extracting the points that do not fit that plane, the outlier points. Combining that with the semantic segmentation, you have a pretty decent set of hypotheses, and that's what you see here in purple. But you can refine that even further because things might have been moved by a couple of centimeters, or just through the noise in the reconstruction, you might be off by a couple of centimeters. But knowing the reference and the current observation, and having reduced the search space drastically already through what we described before, then you can just look for the cluster you detect if there's a matching cluster nearby in the reference map. So typically, you only allow your cluster to move in plane, so translate a little bit or rotate a little bit and see if there's something that can match. And that way, you can remove even further, even more objects and have a much better detection, which you can see here. So in that case, you can see that the laptop was there before, didn't move, but moved enough that it would be picked up by the original method. And if you have this local verification on top of it, then you have a very good set of objects out of place. Very similar to the ground truth, actually. That's a different approach to object detection compared to what I described before with master CNN, because you do not have any class information, you do not have any semantic information, but at the same time, you can detect anything. You're not limited by the class you have learned beforehand. But either way, you end up with some detection from which you can estimate the pose of. So yeah, let's go into the core of today's presentation, which is the object pose estimation. And as mentioned before, that typically starts from a set of points that you assume are part of a given object. The first method I want to present, which is based off something I would call it classical at this point. It was originally introduced in 2010 by Dost, and that's the point pair features, which is a very clever idea that's purely based off geometry. So if you have some depth perception of your scene and some 3D model beforehand, then you can estimate the pose of that object in the scene. And so we'll get into a little bit more into how it works. But first of all, let's define those point pair features. And yeah, for any set of 2 points in the scene, because you have a complete scene and not just 2 points in space, typically you can also estimate the normal of each point through the neighboring points, essentially. So if you have 2 points with their normal, then you can compute what's called the point pair features. And there's, as you can see in the slide, that's the distance between the 2 points, the angle between one normal and the P1, P2 vector, the normal between, sorry, the angle between the other normal and P1, P2, and finally the angle between the two normals. So they're very simple, and you can notice that they're all rotation invariant, which is quite important. So the idea then from this is that independently of the orientation of the object in the scene or translation of the object in the scene, those pair of those features for any given pair of points will be similar enough. They're not super descriptive, but if you have enough of them, the combination of all those votes will give you a good enough pose estimation. So in more detail, how does that work? Once you compute you start with your reference object model. That's the A section over here. And for that object model, you will compute all the possible pair of points. And for all possible pair of points, you will compute these point pair features. You also discretize them, and that gives you this four-dimensional lookup table, again, because we have 4 different point pair features. Now that you have this reference lookup table, you can go to the actual scene you perceived and do a similar process. You compute all the pair of points, and anytime you have something that matches any discretized point pair features, that gives you a potential vote for an orientation. However, there's one last point that's not necessarily obvious, but there's one last point that needs to be solved, and that is how to accumulate all of the votes you have. Because if you just do it in a most straightforward way, you're working with a 6-dimensional space, and that's very large actually to accumulate the votes. But you can take advantage of what is being described by your point pair features, and that is you have 2 points with normals. So if you take one of those 2 points as a sort of a reference point, then that reference point and its normal constrain the pose almost completely, except for one dimension, which is the rotation around that normal. So for any given pair of points, one of the 2 points is considered the reference point. And the only thing you have to save, and with a little trick that you won't really need to get into it, but the only thing you need to save now is what reference point and what angle around that normal you have. And so if you have a matching pair of points between the scene and the model, then you can just vote for that given reference point with that given rotation around it. And that's reducing the problem to a 2-dimensional voting space. That's a lot simpler, and you can do it very efficiently. And once all the votes are accumulated, then you can do that. You can estimate the pose of your object. So actually, this method originally was intended for both object detection and object pose estimation, because if you have enough votes in an area, that also you don't have to limit yourself to a cluster that only has points of the object. However, if you want to be scalable, of course, that's not going to work out well because you need to search exhaustively the entire scene for all pair of points for all object model differently because the lookup table is specific to the object model you have. So the way people have been doing this in the more recent years is by combining this with the mask RCNN type of approach that I introduced before. And so this mask RCNN will give you not only a cluster of points that should belong to the object, but also the class of the object. And so you can use the point per feature approach for one single object at a time, and you only look at the correct points of the object. You know, all the points that you have in your cluster are part of the object, and that makes the search a lot easier. And yeah, to showcase the possibilities of this PPF approach, you can see that in this BOP challenge, so benchmark of object pose estimation, even in the 2019-2020 leaderboard, some variation over mask RCNN plus point pair features ranked second in that BOP. So it's still very powerful. And you can even notice that it's actually, even in terms of speed, it's fairly competitive. One problem it has is that you do require depth perception for your object, which is not guaranteed. There are some objects, depending on the type of approach, type of sensing you're using, and the type of object, you might not always have depth points for it. So I guess the next step is looking at how we could potentially detect objects, purely basing it on the RGB sensing, which is typically you always have your object in the RGB sensing, even though it's not guaranteed to be in the depth sensing. And so a couple of years back, a member of our lab introduced this fixed to pose ID, which is using exclusively RGB images for its estimation at test time, but requires some object model and object pose. Right. It is a learned method and therefore requires training sets to be able to be trained. So first of all, what is it learning it from, the pose estimation? You will need a set of RGB images that are annotated for a given object, and therefore you know the pose of the object in the scene. But the 3D model doesn't need to be textured, which is an advantage because whether you're aware of it or not, accurately texturing an object is not easy. So yeah, once you have that set of objects, the goal of this method is to learn this 3D correspondences directly in RGB space. And so for any given object in the scene, what you will be trying to predict for it is not directly its pose, but for every pixel, the position of that pixel in the reference frame of the 3D object model. So, for example, if you look at this corner here, let's say that's the 0, 0, or that's the 0, 1, 0. Oh, sorry, 1, x being 1, let's say in the red, and 0, 0 on the other two. In the space after rotation and translation, you want this to be of the same value. You're directly predicting the coordinates of that point you see in the scene inside the object reference frame. Once you do that, that actually gives you directly a dense set of correspondences between the points in the scene and the reference object models. And so that means you have correspondences between points in a 2D image to their 3D position in the reference model. And you can solve the problem of the pose estimation from that set of correspondences using something that's called PNP, and that stands for perspective endpoints. Excuse me. And in this case, typically PNP only requires 4 correspondences to be able to estimate the pose. But in this case, because we have many more, we can combine this with runsack to estimate it more robustly. So in a little bit more detail, you can have a 2-stage approach or a 1-stage approach, depending on how you do the object detection. So if you have an object detector beforehand that just gives you a bounding box, then you'll go through 2 poses, where the first pose will be estimating the correspondences as described and the mask of points belonging to the object. This will give you a rough estimate, but through the mask, you actually will be able to use the mask predicted there to fake having a mask detection in the first place. Once you have this first mask, then you can refine your prediction using the mask as well, instead of all the points in the bounding box, and predict again the correspondences themselves. And that you can use for your final pose estimation through PNP plus ransack. So the network used for that approach is a encoder-decoder type of structure with skip connections. And if you have the annotated pose of the object model, then you can automatically create your ground truth colored images. So that's fairly straightforward. Actually, it's this case, so that's the one predicted by the network. So you have simple, well, at least straightforward supervision just by pixel, so that your reconstruction of the correspondences is as accurate as possible, given by the L1 loss. But you can also use, on top of it, a type of discriminator approach, which in spirit is similar to this generative adversarial network. So this discriminator is trying to detect whether the input image is a rendered one or a generated one. And ideally, if it's succeeding at predicting that, then your image's input or your generated image is not good enough. And so you'll be backpropagating until here. And from here on, you backpropagate with the opposite of the gradient, such that you actually confuse the discriminator as much as possible. All right, the final object pose estimation method I wanted to present today is slightly different, but also just work purely on RGB images, and specifically actually is trained purely using simulated images, artificially rendered images. And that's, of course, very advantageous because obtaining the training sets that's necessary for the previous approach is, well, very time consuming. So if you just have a set of object models, in this case with the texture, then you can just render a set of scenes and a set of views for every scene that you can use to train your object pose estimator. However, you might be aware that even the best of simulators still has a gap between what is rendered and what the real world picture will look like. That's referred to as the scene to real gap in object pose estimation. So this specific approach by Repose is actually designed to cope with that gap. One major difference with the previous approach presented is that it does not rely on a separate object detection step. So it's directly working from the RGB image to complete one, and will be predicting the pose and the masks. And you don't need any object detection in the first place. It also detects many different object models at the same time, so that's more scalable, of course, and is reasonably fast. At least in it's 27 FPS on a good GPU. So in the current space, I would say it's competitive and fairly fast. So as mentioned, the method is trained exclusively with artificial data. And one of the ways it is designed to cope better is, well, first of all, good data generation, good data augmentation with a lot of different methods, playing with the different materials, different views, different backgrounds, different everything, as randomized as possible to cover as much ground as possible. But second of all, it's also using what's called a feature pyramid instead of just an encoder-decoder network as before. And it's been shown to perform better under a sim-to-real gap. So you end up with this slightly confusing diagram. Well, the key idea here is actually that your encoder will slowly reduce the size of the feature. The size of the feature vector you will end up with are slowly getting smaller and smaller. But that means that every point in there has a bigger corresponding receptive field. So it actually covers a bigger part of the image. So what you would ideally want to do is that for any given, you will be creating hypotheses for any given scale, and you want to, as much as possible, match your object size to the corresponding scale, such that you can more efficiently predict the pose. Because if you have picture representing a quarter of the image, then it's a lot easier to use that specific feature to predict the pose of an object that also takes a big part of the image rather than a small bit of the image. And the exact design for this feature pyramid is actually driven by this scale ID matching it to the scale of the object, and empirically, of course. And then the way you obtain the pose estimate itself is slightly different, but instead of predicting densely for every pixel the pose estimate or the corresponding position in the reference object model, what you predict is the position of the corner of the bounding box. But you predict it multiple times through the feature pyramid, and so you have a set of hypotheses for every corner. And you again have a set of 2D, 3D correspondences, because those points in the 2D image actually correspond to corners of the 3D bounding box. So you can use a perspective endpoint again to predict your final pose. All right. And so altogether, if you have it running on in this case, that's a Toyota HSR robot picking up objects, you can see that you can pick up a set of objects. It should be mentioned that all the markers on the table in this example are not used for the pose estimation at all. They're used to compute the metrics for evaluating the pose estimation. So yeah. Okay. I think that was all I wanted to present for the pose estimation. Now let's go to the final part, which is what you can do for object pose refinement. Because up until now, we've been trying to go further and further away from the low-level image information to have information that is useful and usable for pose estimation, for object detection, all those object-driven tasks. But that doesn't mean that once you have the information about the object, you can't go back to the lower level sensing to make sure that whatever you predicted makes sense. So comparing that high level prediction to the low and the closer to the sensing itself, the data you have, that's called verification. And if you use that more closer to the sensing type of information to refine your pose, well, that's refinement. No surprise there. And one of the most popular methods here, and fairly standard at this point, is this iterative closest point. So in a couple of words, very simply, if you consider this 2D example of iterative closest point, you have this blue line and the red line, and you would want to align them as well as possible. What you can do is that first, for every point in your blue line, you will try to find the closest point in the red one. So that's what those lines are about. So you create your correspondences by already looking locally at the closest point in the other model. From this set of correspondences, you can then estimate a transformation. And if you apply that transformation, you have a new position for the blue line, and you can repeat the process, looking at the correspondences, estimating the transformation, and eventually you'll end up with something that it will converge to something. So that's very good, actually, if you have already pretty accurate position, because it will make it even better. However, one of the big issues with ICP is that it will diverge if the initialization is bad, and it can make your pose estimation even worse. So we can look at something slightly more clever. And one idea that was introduced, in the robotics and automation letter in 2020 by Weibel, is this idea of combining both the refinement and the verification, and including to all this concept of plausibility, which in this case is shorthand for basically physical simulation in a physical simulation. Basically, is if your pose estimation for a given object is going through the supporting table, well, that's not plausible. If it's floating in the air, that's also not plausible. If it's put in a way that is not a stable pose for the object at hand, that's also not plausible. So yeah, this idea of combining both type of approach leads to combining those two metrics essentially. And so just for illustration, on the left now you have a video of scoring of the pose. So using the normals of the scenes and normal of the object, you can see that you can just compute a simple metric to measure how well it aligns. And so the warmer, in this video, the warmer the color, the better the fit between the estimate. And so the contour is from the estimated object. And you can see that if you just, in this video, we just kind of go randomly, but it's just shown to be a good metric, since the ground truth pose is, of course, shows a much higher fit than any other pose. Okay, that's more on the looking at the depth sensing data, more low level, similar to what ICP could do for you. On the right side, this is an illustration of the physical simulation and how it can help make a better fit for the object. However, just like the ICP and most of the refinement method, the physical simulation is also pretty likely to actually diverge and make your prediction worse in some cases. For example, typically most physical simulation, if you have the object slightly colliding with the table, will kind of explode and project your object real far, which is very much the opposite of what you would want. So the idea that was introduced in this paper is actually, again, as I mentioned, combining them such that they can put bounds on each other, essentially. If you have your refinement that's diverging relative to the physical simulation, then the physical simulation can keep the refinement in bounds, and vice versa, because you don't want to. You typically assume that you have reasonably small refinement steps to take in the first place, and using both of those, you can refine it more reliably and end up with a better pose estimate. But yeah, as I described, everything I've described so far works one model at a time in the scene. So that's still reasonably easy. But if you start considering an entire scene, the pose of many objects will depend on the pose of other objects already in the scene. And so you have to consider, well, number of combination that is possible and should be looked at between potential pose for every object is exploding, and that's not manageable anymore. So the way this approach deals with that is by using a Monte Carlo tree search and clever combination of everything, such that you can actually optimize the pose for everything. And typically, you can consider object pose in a meaningful way by first of all starting with the one closest to the table. And once this one is refined, then you consider this one as stable, and you can look at it as a stable support plane for the next one, and so on and so forth, to make it a lot more manageable overall. Just to conclude, I wanted to mention and say a couple of words about object modeling, because throughout this presentation it was assumed to just exist, but of course you have to obtain this. I think the first thing to mention, as up until now I've only described how to obtain the pose of the object in the scene. However, the end goal is how to grasp that object in the scene. And so, as mentioned, if you have an annotated object model, then you can just use the same transform that you have for the object model to transfer your grasp approach and grasp pose from the reference model to the scene, so that you know where to send your end effector to grasp the object. This can be obtained in a couple ways. If you work with a simple gripper, like a two-finger grippers, you can just simulate it, and that whatever is stable as a grasp is kind of good enough, and that's simple and fast, and so you can just straightforwardly automatically compute it for every new object model you have. That's nice, but of course fairly limited. It's not necessarily the most accurate, because physical simulation has all sorts of problems, and it's the more complicated your gripper, the less likely it is to give you good grasp point estimates. Of course, that also doesn't give you any semantics, because you still don't know how to grasp your object for your mug if you want to make sure you don't pour any liquid out of it while grasping it. So you can have it you can learn in a different way, for example, by observing human grasps. But then the question is how to transfer from a human hand to a robotic gripper. And so depending on your gripper, it's more or less complicated. You can simplify it by just assuming that we pinch things. If you have if you want to transfer to a two fingers gripper. I've put down there a reference to just a way that learns that mapping from human hand to robotic gripper. Second aspect of modeling is, how to obtain the model themselves. And I won't go into much detail, but I just wanted to bring up all the challenges of it. And I'm sure many of you in the room are aware of the trickiness of modeling. So obviously you can model everything by hand in a modeling software, but this requires people familiar with the software, and is still reasonably time consuming. But you can obtain very good models. Ideally, you would want to be able to obtain the model from the same sensors you use for the pose estimation itself. But there's two major issues that you're presented with if you try to do that, and that's first of all how to obtain a reliable camera pose, because you will have to combine many views, and how to obtain high quality data for every single view. So for the camera pose, fortunately, if you can already have the object somehow in the robot hand, then you are in luck, because typically in most robots, you have sensing in every actuator, and if they're of reasonably good quality, then you have already a good enough transformation to actually model the object directly in the hand of the robot. You can also use, as illustrated in animated picture on the right, some even more accurate robots, or I even say industrial robots, to capture many views, and those are super precise. And if they're well calibrated, they give you fantastic camera poses. But if you're out of luck and have to estimate it, then you have a couple of odometry, visual odometry methods, navigation methods. They're not quite there if you want to just obtain object models or high accurate object models, but it's very active field of research, and if you're interested in it, I encourage you to look further into it. For the data sensing, well, there's not much you can do besides relying on your sensor, of course. But yeah, I think I'm getting close to the time itself, so I'll leave it at that. The better the sensor, the easier the task, of course. And yeah, I think it's time to listen to your questions. Hopefully you have many.